Next. Next, we have Shenlong Wang. He's an assistant professor at UIUC, Department of Computer Science. His group's work focuses on algorithms to perceive and model the 3D world, creating realistic physics-informed simulations based on real-world observations and exploring the application of modeling and simulation techniques. So, Professor Wang, are you sharing screen right now?
Yes, I'm sharing the screen. Can you see the screen?
Yes, we can see it. Yes.
All right, and can you hear me clearly?
Yes, yes.
All right,
Yes.
great. All right, great. Thank you for the introduction and thank you for having me here. And similar as some other previous speakers, due to visa issues, I'm getting stuck in US, and at this moment I'm zooming from Hawaii while attending the ICCV. And I hope you can still enjoy the remote talk and can see we can have still an engaged discussion. All right. And my talk here is about how to create interactive war simulators from videos with applications to robotics. All right, so as some other previous speakers already mentioned, that we are working hard on making good progresses towards an exciting future where generalist robots can support everyday life, from cooking to housekeeping to delivery and healthcare. And I personally believe this is the best time to choose to do robotics. And the technology is rapidly advancing, and its real-world impact is emerging now. And to achieve the goal, our robots must be able to engage in very complicated physical interactions with human-designed tools and objects. For instance, tasks like opening drawers and handling dishes or wiping surfaces that requires rich interactions and manipulations and force control and real-time physical reasoning. And on the other side, generalist robots must be able to operate in unfamiliar environment like a new kitchen or hotel. And that also requires understanding the layout, reading signs, adapt to spaces that designed for humans, say using the different tools that in the kitchen and in the open space and not originally designed for robots, right? That said, are we there yet? I personally believe that we haven't been there yet to achieve all the desired things, right? As this workshop has been nicely designed for, right? We are here discussing one of the biggest obstacles, as mentioned by some other previous keynote speakers and also the high spotlight speakers, right? The big obstacle here is a demand of large robot data. So getting high quality interactive data is simply hard. So on one side, it's real world video demonstrations and pre-collected logs. They are realistic, but they are super expensive to collect. And it's simply, they are just open loop logs, right? And on the other side, we do have computer simulations, right? For decades. That being said, simulation faces the challenges, the very well-known challenges, the so-called sim to real gap, because physics are not really realistic, and it can be over simple, and they might not be as diverse, and it's just because it's super costly to make it to be as complex as a real world environment that show on the left, right? And here we can see that both real world data capture and the simulation, they do have their pros and cons. So what I can do. So in today's talk, I'm trying to advocate a new paradigm that I believe some other keynote speakers like Suyan also covers, right? The key idea is trying to build simulator from just a piece of video captured from the real world, right? The general idea is straightforward. So given the input images, and we'll infer the physical properties of online 3D world, reasoning about its semantics, geometry, and physics, essentially any attributes of the scene that matter for our prediction. And then we are able to build a so-called interactive scene representation. And after we get these scene models, we'll also leverage another path that we will run physical simulation to update our world. This is a digitalized version of our real world, either using generative model approach or physical-based approach, and then using a nice generative or physical-based renderer to produce a final edited and counterfactual yet photorealistic video footages, and then to answer the what if questions, just like a real simulator can do. So you can see the idea here is trying to combine the best of the two worlds. It leverage a real data to promote the realism. And it also leverage the benefits of simulation because in fact it's a simulation happens in computers. So it can be very inexpensive and it can be closed loop. So the key technology here, you can see that, in order to enable, to make every video to be interactive and to be simulatable, so we need two things. The first is we need a good 3D representation that can facilitate both physical interaction and the second is about physics. Just like a simulator, we want it fast, but we also want to be accurately reflect what can happen in the real world. So let's see how can we achieve that. Okay, a very natural question is, does existing 3D computer vision algorithm alone will do the job and give us a simulator? Is that the case? So here we show 3D reconstruction of UIUC's kitchen by just my student taking a short video. I think it's like 30 seconds or something. You can already see the 3D reconstruction algorithm, very modern 3D reconstruction algorithm, can really give us very good geometries. You can see that all the details are there, the meshes are clean, and it looks great, right? That being said, they still fall short when it comes to understanding the physical interaction. So taking the zoom in part in the right slide as example. So it's a 3D reconstruction, but you can see that the kettles and drawer surfaces are tightly connected to each other part of the scene. So in other words, the entire scene is just one big mesh. The system does not really know whether the kettle can be lifted up and actually the drawers can be opened. So those real world interactable capacity is not there, right? If you take a look about the top part of the right component, you can see there is a paper cup, right? We know that in the real world, the paper cup can be bended, but in practice, they are just a solid mesh. They does not really exist such a physical interaction. So this is a gap that I hope that throughout the works that I talked today, we kind of make a step towards bridging this gap. Okay, so in today's talk, I will cover two works towards building a simulator from video. The first aims to build articulate objects and rigid body digital twins from just static video. And the second aims to build interactive digital twins of soft body objects like clothes and toys and so on and so forth. So now let's come back to the kitchen example. Assume we are in this kitchen and we cook for breakfast, right? What are the things that will most interact with? If you take a deeper look at this one, right? You see that all the utensils and all the foods are not really present in this thing because we mostly hide them into the cabinets and into our drawers and stuff like that. So obviously those drawers and doors and handles, they are everywhere. And those articulated object components, they are essential for accessing storage, appliances, and tools and making them to be central to everyday tasks. So underlying the kinematics and underlying articulation is very much the key to functional world modeling. So that leads to the first project that I will cover. Given a video of a static scene, we will reconstruct a physical interactive digital twin. All the drawers and doors now can be virtually opened, allowing us to simulate what-if scenarios and visualize the outcomes. So as you can see that although the input video is just about the static scene, there's no interaction whatsoever, but the output is a fully functional articulated replicate of the real world environment. All right. And now let me talk about how can we achieve this. the very first question is what type of representation we are going to use, right? That is the very first question that we'll ask for every 3D computer vision project, right? For folks who are familiar with Gaussian splats, we know that the Gaussian splats can render photorealistically. Like this image I show here is in fact coming from a novel view, which is, you can see the quality is actually quite decent. That means that when it comes to geometry, Gaussian splats really is not really doing well because it's optimized towards rendering objective only. So you can see that it does not really, if we convert the Gaussians, the same set of Gaussians into iso surfaces, it looks terrible. It does not really good for physical interaction. The surface geometry sometimes it's just, not accurate. So the quick summary is it has good visual fidelity, but it's not good for physical interaction. On the other side, we know that there's another representation called neural SDF, right? Like news and other stuff, right? So neural SDF is the opposite, because it models the geometry explicitly using a signed distance field. So it has beautifully clean geometry like what I show here, but the texture, if you take a deeper look, right, they look a little bit dirty and they are really suboptimal. So our goal is, can we combine the best of the two worlds? So, and how can we achieve that, right? We'll first, since we know that neural SDF has good geometry, then we'll first reconstruct the accurate surface with neural SDF. And then we'll just anchor those Gaussians around. Around means that we'll make the Gaussian to be very close to those iso surfaces, but we still allow some flexibility for the Gaussians to move here and there so that it enables some flexible optimization so that it still can optimize and to keep the high quality rendering. And then each Gaussian can be attached to some surfaces, to some triangles, and then the movement of the triangles can drive the movement of the Gaussian, which can be used later for physical simulation. And by combining this and then building such a dual scene representation, we are able to get the best of the two worlds, good geometry and also high visual fidelity as well. The next question is about, how can we interact with the scene? How can we open doors? How can we move things, right? And then to make the scene to be interactable. So the very first step is actually to decompose the scene. We know that the scene shouldn't be just complete and shouldn't be just a piece of mesh, right? Well, first identify each, actionable and interactable object. In this work, we'll focus on some of the rigid body objects, such as bottles here, or cups in the sink, or items on top of the microwave, and then also, some articulated objects like openable cabinets and openable drawers and stuff like that. And then we'll try to infer those physical properties of those openable objects and rigid body objects. We find that surprisingly rich prior knowledge about physics has been encoded in GPT already, right? Which we can just send them the images and highlight each instance, and then ask them about some questions about physical properties, and then they are able to get a pretty decent answer about those physical properties of the object using common sense knowledge. For instance, that it knows that cabinet doors are revolute joints. It knows that this drawer is a prismatic joint, and this bottle is roughly 1.5 kilograms. And using that, basically, we are able to assign those physical properties for each object that's supposed to be interactable. And then the very next question is, what happens if we open the doors, right? We never seen what inside the drawers. We don't know the interior, so we can leverage the journey model to imagine what naturally will look if we open the doors. And here is basically some of the interiors that we'll imagine that what it looks in terms of geometry. And then we can also imagine what it will look in terms of appearance. And then we'll just bake them into the 3D mesh, some of the rich textures, and we can even bake them as a Gaussian splat textures so that we are able to not only just, get complete part from a visible component, but also the invisible component. And that basically completes the entire pipeline. So given multiple pose images, we deploy a dual representation, and then we'll animate the scene with physical reasoning and estimate articulable and movable objects. And then we will complete the 3D shape of all the hidden regions and texturing them. That enables us to create a fully interactive digital twins that supporting real-time physical interactions and rendering at the normal views. And this is the work done by my PhD student Hong Chi. And yes, you can see that on the background, on the whiteboard, this is me together with some cute bunnies and cute, cats and stuff like that. You can see my students really know how to get themselves well motivated, right? Their encouragement coming from their advisor and also some cutie animals. All right, and here is the results of interactive environment reconstruction. Note that all the videos, they just captured with purely static video. So just static the scene, no interactions, but we are able to simulate a complete scene with drawers and doors open. I apologize about some artifacts. This is a known bug that from Mac and Microsoft, but our reconstruction is actually quite clean. All right, and here is some of the quality results compared against some other works that doing articulation reasoning just purely from 2D images. You can see that the 3D grounding that proposed in our work can really help to make the articulation axis to be accurate and basically the faces to be accurate and articulation type to be accurate as well. One alternative approach about, building the articulation from the real world video is instead of creating so-called digital twins, we are doing basically generative approach or retrieval based approach. So the goal is let's just get a functional similar scene. We don't have to stick to, original textures whatsoever. And some people refer this type of approach called digital cousins, right? We do some comparison here. You can see that although, they get some functional reasonable output layout, but you can see that it does not really replicate the original environment. So it significantly increase the scene to real gap. But here we definitely, by combining both, we basically benefit from significant closing the scene to real gap, although the inputs are still the same, just coming from the same input videos. And since our articulate body and Gaussian rendering are all real time, we are able to create a real time, game. Here we build a first-person shooter game and deploy that into Unreal using our created articulate body. So you can see that, Hongchi controls the first-person actors. They can open the doors and can shoot basically balls around and find some of the hidden items in the drawers. And of course, since this is a robotics workshop, we also want to showcase how we are going to use that for robotics. The key idea is we are going to build a digital twin of our kitchen, and then we're just trying to do reinforcement learning based agent, and then trying to allow the agent to explore and train how to open different doors and drawers in that kitchen repetitively. And then in a zero-shot effort with no real-world demonstration, we can already deploy that robot into that same kitchen and then to open the doors. You can imagine that in future, if we want to deliver a household robot in our kitchen, we just want to take a video of our kitchen, and then before it had been shipped into our home, the robot already repetitively rehearse in their mind or in a computer about how to do jobs in our kitchen. And when it was deployed in our kitchen, we already know every details about our kitchen and it can do the job in the first minute. All right, that is our goal. And this is how we are going to use real to sim to real pipeline to benefit the robot learning approaches. All right, so next, basically, we want to move from the kitchen to a bedroom, say my daughter's bedroom. So basically, if we see here, we see tons of things, right? We see soft toys, we see bed sheets, and we see pillows and teddy bears and Mickey Mouse and you name it, right? After our robot to help prepare our lunch, we might ask a robot to help to organize our bedroom, right? In order to do that, we have to handle and interact with a certain object that is a deformable objects, right? They are also everywhere here in our bedroom, right? How can we deal with that? So here in this work, we are trying to answer this question. Here on the left is our input video. Still, it's basically a video about where the humans are interacting with those soft body objects, like this rope and these stuffed animals. And then in the middle, we see our 3D reconstruction. We are able to reconstruct a decent geometry, and we are able to track the movement of the object, and we are able to understand the action of the human hands. And then on the right, we show a photorealistic and physical realistic digital twins that can replicate the input. We do overlay between the digital twins and our observation. You can see it can perfectly replicate the movement. But what is more important is not only just replicate or track the observation, but also to be able to answer what if questions. So here we still use a dual representation paradigm, and the general idea is basically on the physical side, we use something called spring mass, where the soft toy is represented by a set of mass nodes that can sense external forces such as user interaction, gravity, friction, and contact forces. And then each neighbor nodes, they are connected by some elastic springs that models the internal forces that makes them to allow them to deform, while in the meantime, it does not really, it can forbidden them to be broken apart. Right? And then we still use Gaussians to model the geometry and appearance, and then we attach the Gaussians into nearby nodes so that the deformation of the nodes will drive the deformation of the Gaussians. But the Gaussians can encode the rich appearance to replicate the realistic images and videos. Now, given this scene representation that and also an input video, and we are able to optimize those physical scene representation to jointly reason the geometry, physics, appearances. And the high-level idea is if we get a really good digital physical twin, then given the same set of user interaction input, it should be able to reproduce our observed RGB video. It should reproduce our observed motion that can be used by some whatever motion tracking algorithm. And also, it should be able to reproduce the observed geometry that coming from multi-view geometry or depth sensing, right? We'll optimize those three goals jointly, and also we optimize all the parameters, including both the spring mass parameters and the Gaussian parameters jointly in an edge minimization framework. Essentially, it's a joint inverse rendering and physics pipeline. And then we'll get the resulting Gaussian topology and physical parameters, like the stiffness of the spring. Then our resulting physical digital replica is highly complete. You can see the entire toy is complete, although it just from very sparse view, like 2 or 3 views. And our digital twin can be interactable in real time on the decent GPU and can be physically plausible. Here, I think our digital twin can run at 1080p resolution on 4090 with more than 50 FPS. All right, you can see how realistically interact with the user input, and also how realistically interact with the table, basically the contact and so on. So we can showcase that it can diversify to different stuffed animals, and also clothes, and also ropes, and so on and so forth. Here we show another example where we use teleoperation to operate these claws. And then in the meantime, we record those actions of the robot, and then we replicate them in our physical digital twins in the computer, and then overlay with the real world footage. You can see how close that our digital twins can replicate entirely novel action and in real time. And that also allow us to do robot manipulation. Here, basically, given basically that slot, we want to put the rope on that slot, right? In digital twin, we are able to unroll different actions and then trying to come up with a good action to be able to achieve that. And then in the physical world, we see that the same outcome happens if we figure out a good action in the physical simulation. And here is another example. Still, we are using
Sorry, a gentle reminder, we have 5 minutes left.
Sounds good. I will finish that within 5 minutes. And we are able to unroll given a set of actions, we are able to use our digital twins to do prediction. And then we are able to use a model predictive control policy. It's a learning-free policy, just evaluate different actions and which action can lead to the final outcome of basically to make the clause folded. And then we are able to successfully achieve that. And here is another example. The target is like a S shape of rope, and our MPC policy can easily achieve that as well. All right, so feel free to play our demos and from our website, and our code is available. All right. And with that, that basically summarizes our approach here I talked today towards building a physical world simulator, from real world videos for robotics. So I would like to share a few take-home messages that we found through doing those type of works. So the first is, what is a right scene representation, right? So often you get asked these type of questions, right? You have to choose a digital representation of the scene or object. So the answer is obviously, like for many people, we know that there is no right 3D representation. All the 3D representation is approximation of the physical world, right? So each 3D representation has its pros and cons. The general principle that I learned from doing this work is we'll just let each 3D representation to do what it's good best at. And then we do not really worry too much about the discrepancy between those 3D representations and simply trying our best to make them live together. All right. And another, take-home message that I believe is interesting is about how to infer physics. You can see from the first work, we heavily rely on some common sense prior knowledge that encoded into foundation model like GPT. GPT knows basically how heavy this water bottle is, and GPT knows that the drawers should open in this way, doors should be open in the other way, right? But in the meantime, for some other type of objects, we might rely on observed, basically interact them, and then observe those interactive outcome like soft body, and then using inverse physics. I still think that combining the best of the world is still necessary in order to get accurate physical digital twin. And the third is how can we use this physical digital twin in order to benefit robots? From a training perspective, yes, we are able to use real world videos and then convert that into a simulator, and then trying to generate tons of on-road closed loop, episodes, and then to do reinforcement learning based, simulation. But in the meantime, once we get a physical simulator of the real world, that can also be a good model-based predictor. And then it also can allow us to do MPC type of work. All right, and for the sake of time, I'm going to skip the future work, but in general, we should in future, we should really think about how can we also leverage generative model and to combine with physical-based modeling. And second is how can we, scaling up our digital twin simulation to also any scenes, any physics, and to be 100% fast, right? There are quite a few other type of physical phenomena that my group have been doing, but I don't really cover here in today's talk. For instance, rigid body dynamics, weather dynamics, and some other type of soft body dynamics and lighting effects, and today I talk about articulation, right? So all those videos basically share the similar principle about real to scene representation, basically building a physical simulator from the real world videos. All right. And with that, I would like to thank all my amazing students and also my collaborators and also the funding agencies. And I'm happy to take any questions from audience if time allows. All right. Thank you.
Simon, do you have any questions from the audience? You might be muted. Oh, you are muted.
Yes, there was a great round of applause. And please, if you guys have any questions, please raise your hand. Meanwhile, while you guys are preparing questions, can we have the oral speakers come to the first row? The four papers. Yes, so who has questions? I'll repeat the questions.
Yeah, thanks for the talk and your nice presentations. I just have a specifically impressed by your controllable objects movement or direct. So my question would be like, how you balance the realism actually your how do you compare that with the real world? How do you validate which one's got? See if you can validate the movement or trajectory of the deformed object compared with regarding like the visual realism, and etc. How to be validate.
So the question is,
how do we evaluate the realism of the string?
I see.
How do we evaluate the gap?
so the question is, how do we evaluate the difference or evaluate how real the
Okay.
digital twin is?
Yes.
Yes.
This is an excellent question. That's always come into play, right? So there are two different approaches that you are able to tell whether your digital twin is accurate or not. The first is through resimulation performance. For instance, if I have a rope, I can record 3 or 5 different videos of interactions, but I only use one interaction to do 3 reconstruction. And then I'm going to replicate the actions of the other videos. And I will see whether my physical digital twin can replicate the consequences of those actions, right? And that is basically sort of ground truth reference. This is a way to evaluate the resimulation performance. Usually it can be done through a motion tracking and also can be done through rendering if you really care about the rendering performance. And another one is really about how your digital twin can benefit downstream tasks. This is usually what I value most. So that can be done, say, assume that you have different versions of those type of digital representation, try to use them to create data for you to train the same reinforcement learning agent, or try to use them to do prediction for your MPC policy and see which one works better. So I think ideally we will combine both. From a 3D computer vision researcher perspective, I care more about the first. From a robotics researcher perspective, I care the second more. Yeah, I hope that answers your question.
We'll take one more from the stage. Could you pass the mic?
Yeah, my question is.
Do you want to just come up because it's easier to get your voice across here?
All right.
So the oral presenters for the next section, can you raise your hand? Who is the first?
I speak into this microphone? Or...
Yes.
All right, I hope you can all hear me also.
Yeah, I can hear you. Yeah.
Perfect. So my question is about how much you think that the physical realism actually matters. Because I think in your deformable objects, you use a quite simplistic material model.
Yeah.
But you still show that, it could successfully transfer the policies, even though the simulation was maybe not perfect.
Yeah.
So.
That's an excellent question. It really depends on, the downstream application. Here, I think the physics interactions, they are simpler enough that it can tolerate some of the inaccurate physics. But I still believe that for more complicated tasks, such as I prepare some meals and stuff like that, I guess having an accurate physical digital twin matters. For training, physical digital twin might matter less than MPC framework, because for training, we can benefit a lot to get a more robust policy by diversifying a little bit physical properties. Actually, domain randomization might actually help a little bit. That being said, for say accurate open doors and open drawers and those type of stuff, of course, we need to get the right articulation. And for lifting objects, we also need to get a good range of masses and frictions. That being said, for those type of parameters, we might have better tolerance as well. So my simple answer is depends, right? Depends on the downstream task and depends on which physical property you might want to model. Yeah. Mm-hmm.
Thank you.
Great. Let's thank Professor Wang again. It's a round of applause.
All right, thank you. And if you have any other question, don't hesitate to reach out to me offline. All right. Thank you for the invitation.
Yeah. Okay.